Hello everybody, my name is K.D.E, and this presentation is going to be on kernel density estimation, or K.D.E. I'm going to talk about what K.D.E is, why you might want to use it, along with some history. I'm going to go into some deeper details of the theory, along with some code, also applying K.D.E to do some data. So when studying statistics, it's easy to learn about normal distribution or Poisson, but encountering variables in real life, they tend to not follow such simple densities. So it makes sense to try to estimate some density when you're doing some research on some data. Looking at the histogram on the left, it's the time between eruptions for Old Faithful at Yellowstone National Park, and the density seems to obviously not be some simple unimodal density, maybe some mixture of normals. But changing from a frequency histogram to a density histogram, applying some K.D.E to it, you get to see this other picture that sort of shows a density that's clearly not something from a textbook. Looking at the history of K.D.E actually goes back to Carl Pearson with histograms. Rosenblatt went into the continuous estimation of a density. Whittle explored the implementation of a kernel function, and Parson looked into the consistency and asymptotic behavior. So the problem with histograms themselves are that you don't really know what the perfect number of bins are. The histogram on the left is the default. On the right, there's a break set to 20. So what can we do? We can use a recommended formula that you see here, but given this data set, the formula will tell you to use 10 bins. And looking at 10 bins, you see this right here. This seems to be the fairly unimodal, smooth distribution, but if we look over here with 40 bins, you see that there's these peaks right here, 1, 2, 3, and so K.D.E has this bonus of when combined with histograms, you get to sort of double check this sort of guessing game where you're trying to determine the suitable number of bins for the histogram. So let's look at some theory. So intuition of K.D.E is such that you have this function that estimates the density, and you see this little x here and the big X here. And it's kind of confusing at first to people who aren't too familiar, but we could just take a look at a simple example with two observations. And you see here that just summing the kernels for each of the observations and taking the average. So at point x equals 0, f hat is basically the density estimation at point 0, and you just do that for all the points on the x-axis. So parameters of K.D.E, there's two. There's a kernel function, it's not so important, the bandwidth, which is what's worth paying attention to. And here on the left, you see a single bandwidth with three different kernel functions, all pretty similar. On the right, what you see is you see three different bandwidths for a single kernel, and the difference is pretty extreme. So what we're looking to do is optimize the bandwidth for some h. A way to understand the math behind this is really this ISE right here, which is the integrated square error. What it's doing is it's taking the square difference between the model and the true density. The expected value of this is the MISE right here, the mean integrated square error, which comes out to a formula for something familiar from math statistics, which is the mean squared error. And the trick is to basically subtract this expected value and add it here to allow you to FOIL this, which will lead you to the variance and bias terms. These variance and bias terms are approximated using Taylor series approximation. The result is this AMISC and this little o term. The little o term is a leftover term from Taylor series approximation, which is an error term, so it's not of interest. And what we're going to focus on instead is the AMISC. And the AMISC, what happens is you get this function of h right here. And the only problem with it is that there's this roughness of the second derivative of the f, which is the true density, which is, of course, unknown. So there are approaches to handling this. There's cross-validation with pseudo-likelihood and unbiased cross-validation. not very good, but we're going to take a look at them. There's plugin methods with the Shether-Jones, the Silverman for the pilot bandwidth, and that's the ideal method, and we're going to focus quite a bit on that. And there's the maximal smoothing principle, which is more of a guideline. So the cross-validation function, what it does is it gets the fit for an observation minus the observation from the model. The thinking being that if you exclude that observation, you avoid the trouble of overfitting on the observation. And we could take a look at the code really quick. You have the CV matrix, and that matrix stores all the values for all n observations for the variable. K.I.J matrix, that's the matrix that you reuse to perform this calculation for each of the n observations, and then you reuse this matrix by resetting them all to NAs. For example, here, we look through all n observations, and then for the ith observation, you calculate n minus 1 values right here, where you're excluding the ith value, calculating the kernel, saving it to K.I.J, and then saving the value to the CV matrix, and you reset the K.I.J matrix all to NAs, and then go on from there. So we have pseudo-likelihood and unbiased cross-validation. So the pseudo-likelihood takes the product of all those cross-validation terms. The UCV, what happens is you take the summation of all those cross-validation terms. The pseudo-likelihood, the issue is that the results are too wiggly, the bandwidth is too small. And the problem with UCV is that the bandwidth is too large. So they're interesting, but we don't actually use them. So the plugin method is what the focus should be on, because we're going to be relying on a pilot bandwidth, which comes from the Silverman method, to estimate the true density. The reason why we like it so much is that out of all the methods that could give you such good results, this is the simplest way to calculate a bandwidth. And so with the Silverman method, what happens is that you replace the true density with a normal, which gives you this relatively simple calculation. The issue with the Silverman method is that if f is a multimodal, there's going to be some oversmoothing. Looking at the Shether-Jones method, we get the RF del prime, and we estimate it, right, using K.D.E. So the K.D.E, what it is it's this f hat term. We take the second derivative. So instead of the f second derivative, we take the f hat second derivative. And we're going to look at a closed form solution for this. So the roughness function is just the inner product of some function. The squared summation right here is when you take the square of the sum terms, you get a set of diagonal terms in the upper and lower triangles. So looking at this matrix, you get the diagonal here, which is when I and j are equal, 1, 1, 2, 2, n, and you get the upper and lower triangles when I less than j or I greater than j, for example. So you get this function of them. So rather than taking the product, like you see here, you're going to take a function of the ij terms, which is what's happening down here in the RF hat double prime, going from a sum of squares to this diagonal section in the upper lower triangle section. So the normal kernel is going to be the kernel that we're going to focus on for the kernel L, and this is simply just the second derivative. So applying that second derivative of the normal into the RF hat double prime, we get this, which is, it looks pretty big, kind of scary, but we're just going to focus on the upper and lower triangle, right? The reason is that for xj equal to xi, you're going to get the diagonal. So we could just reuse the closed form solution for this to calculate, like in the previous example for the h function, we're just going to apply the entire thing to all the ij elements. So what happens here is we move the exponentials together and change the 1 minus z squared terms and set that as a. And so the exponentials, once putting them together, you get this polynomial degree 2, and completing the square, you can separate them like this. So once you get this set of exponentials, you can split the exponentials up again to get this term in here and everything else, which are all constants, as a b that moves outside the integral. So we get left with this c term, right? And so what does it look like? Using this trick where you just change this to a 2 times something, -1 or 2 times something, you get this normal distribution right here. You get the mean and the variance, right? But we're missing this constant d, so we add that on while subtracting out the b, which is just a constant, right? And because we could just add that back later. So what C prime is the expectation with respect to G for A, where A is some 4th degree polynomial. And once we calculate these terms using limit-generated functions for x to the e to x first power, second, fourth, third, fourth, etc., you get back C by using this formula here, where C prime divided by D multiplied by B, and you get this original C over here. And so alternatives to this closed form solution are software packages or Monte Carlo integration. Software packages are simple in that you just have to read the documentation. Monte Carlo integration, there's actually some trickiness to it. So here's a quick overview of Monte Carlo integration. So we have an integrand of some function h, right? But instead of finding that out, we're going to approximate it by changing it to some expectation of some function g with respect to f, where f is some uniform. And so the only issue in our situation is that the bounds are infinite, right? So we're just going to approximate them using large numbers, -10,000 and +10,000. And looking here, we see the function for Monte Carlo. And so we see this outer function here, which is applies this L double prime times L double prime for xi, xj, and it later takes the sum of them, of all those terms in the matrix, after applying the function to the ij terms, and it takes the average, right? But the issue is that this output here, it could actually become 0, and Shether-Jones, when you get that calculation, you're dividing by 0 in R, and the result could be infinity. So what's the issue is that because of the kernel function, the domain for non-zero terms is relatively small. It's even smaller than -4 and 4, right? So when we're sampling from the uniform, sampling from such huge bounds like -10,000, +10,000, there's a relatively small chance that you're going to get some value in there. So this is a conflict between Monte Carlo integration theory and the kernel application, right? So what's a trick that we could use? An ad hoc solution, we could just force one of the terms, for example, the first term from the sample to be 0, for example, just to get a positive non-zero output that we could use for our approximation. Right, and maximal smoothing principle is something different where we're trying to get a guideline bandwidth to avoid the case where you're getting too narrow of a bandwidth that has under smoothing, and so you pay too much attention to false modes. This is a really simple calculation too. And this is just an overview of what the kernel functions look like, right? So you have, most of them actually look relatively similar, and the normal is different in that it has infinite bounds for it. And the uniform is unique in that it's sort of a naive kernel, right? Because the output is just, if you look right here, just 1/2. So another issue is scaling bandwidth. For example, we fit some bandwidth using the normal kernel and the Shether-Jones method. And so this bandwidth that you get won't work for every kernel. You have to scale them using this formula right here, or delta of some kernel where delta is equal to this value right here. On the left, what you see is actually, you saw it before in the previous slide, where it's the same 3 kernels with one bandwidth, but after scaling here on the right, you see the same 3 kernels where the bandwidth is scaled properly. So you see the situation where the fit is actually really close to the normal, and the only difference is the naive uniform kernel, you still see this exaggeration here. Now we're going to look at some data sets where we apply K.D.E. But first, let's actually look at some notable applications. Here in Emery and Carter, you see a group B and group A. This is for babies who die from sudden infant death syndrome and their transformed mass cell count. So group B are infants who died from other causes, but looking at the K.D.E for this variable, you can see that they're clearly different, right? And so this is an example of exploratory data analysis where this insight leads researchers to further clinical investigation on this variable. And here in Boyer in 1980, what you have is an engineering application which is a height in microns of above some arbitrary point for some metal, right? And so previously they thought that this would be a symmetric, but there's actually a slight skew to it, right? And so if it's to the left, that means that it's brittle. If it's to the right, it means the metal's going to rub. And so later on in further research, they start modeling it with something else other than a symmetric Gaussian like they used to. And here in Elgamal, this is a more modern application where there's actually quite a few citations for this. And so they're using K.D.E not for exploratory data analysis, but actually for video surveillance, where they apply K.D.E to each of the pixels in the video surveillance and measure the threshold. And according to some threshold, they'll separate the foreground from the background. So in the application, we're going to look at some pipeline for K.D.E, right? We're going to choose a suitable histogram, then we're going to use cross-validation, then Schieffer-Jones, and then going to find Terrell's bandwidth, and then we're going to scale them, compare bandwidths, and then make a choice. So the first data set is female Pima Indian diabetes, which is basically a data set for predicting diabetes in female Pima Indians. The variable of choice in this application is just the age. Of course, in real life, you want to look at all the variables, but this is just for expediency purposes. So looking at the default histogram, right, it just looks like a skew, but the K.D.E curve seems to outline this extra hump here around 40 years of age, right? And so using a 32 bins, you see this much more distinctly, right? There's a skew and then a hump right here. So using cross-validation, the pseudo likelihood gives you pretty poor results. Just see this zeros, right? All zeros. So what's happening there is, since there's 700 observations and the cross-validation output is between 0 and 1, what R does is just products them all together, and that just results in 0 because the number is so small. On the right side, you see the UCV values, right? And it minimizes around 0.2, giving you a UCV of negative 0.1. And this actually leads to some pretty erratic bandwidth, but compared to the pseudo likelihood where all the values are 0, maybe it's not so bad. But this is just to take a look. It's not for a real application of it. Like, we're not going to use this bandwidth. So Schieffer-Jones use the packages along with Monte Carlo integration and also using closed form solution. The Silverman is 3.2. The packages give a range. Mass gives you the largest, but log fit is interesting because that's the one where I actually get to input the Silverman bandwidth. So that gives you 1.67, and that's really close to the closed form solution. Monte Carlo is relatively close to 1.5. And maximal smoothing principal gives 3.56, which is largest, and this is what you expect according to the theory. And scaling them, you get these different bandwidths down here. And like you've seen before, they start to fit really close to the normal right on top of it. It's hardly noticeable. The only difference is the uniform, which is kind of exaggerated because it's a naive kernel. In truth, all the kernels that are used frequently, they're all pretty similar in terms of their efficiency. So the final choice that we're going to use is just the one that we started with, the Schieffer-Jones and the normal kernel. Looking at the final output right here, you see there's this hump, and the bandwidth allows the K.D.E to make note of it. The other ones tend to smooth this out a little bit. And just to do a little more inferential statistics, or just looking at the data a little bit closer, you look at this group, which is negative for diabetes, and this group, in red, which is positive for diabetes. And at 40 years of age, there's a much more noticeable, right, connection right here. It's not like a subtle bump. It's actually a pretty big area right here compared to the other case where it's just, some skew. So this is actually an example you might want to think maybe perhaps, maybe because when they get older, there's a higher chance for the body to get weaker, then to exercise, to get tired, so diabetes develops, something like that. So that's what it's for. And second data set we're going to look at is the wine data set, where the quality of the wine is being we're trying to predict it based on certain other variables, where these variables are the chemistry of the wine. And again, we just choose one variable because for time reasons. And the one we choose is the volatile acidity. Here you see it looks like a unimodal distribution again, but the K.D.E shows us two bumps right here. And setting m equal to 30, the bins exaggerate much more this difference in the density. Again, the cross-validation for a pseudo-like gives you results that don't really work well, because with a negative bin values it minimizes, but for some small values it spikes up and the rest are 0. So that doesn't give you any useful information. The unbiased cross-validation, however, it's a bit better because you see this minimization around negative 1.6 for 0.04 bandwidth. And this gives you another bandwidth here that looks pretty nice, but it's a bit smooth compared to what we were looking at earlier. And that's sort of what you expect from the theory. Looking at Shether-Jones, we get the Silverman bandwidth, and then the packages, Monte Carlo approximation, and the closed form solution. They're all pretty close here. 0.3. The outlier so far has been masked, but these two packages have arguments. I didn't really take advantage of them. I just use it in this locfit package. So that's probably the best explanation why. Looking at maximal smoothing principle, you also see is 0.46, which is the largest, which is what you expect. And so scale limit bandwidth, you get these results down here. And like before, they all follow pretty close to normal. And then the uniform is the one exaggerating because it's more of a naive kernel. The final choice is the same thing. We just stick with the Shether-Jones, the normal kernel, right? Applying it to the variable, you see this exaggeration of these two peaks right here, with the bins sort of reinforcing that the idea that there's a multimodal distribution rather than unimodal distribution. And then splitting the wine into two groups, arbitrarily choosing quality of 7 or higher as good wine and 6 or lower as bad wine. So the good wine here is in red, and the bad wine's in black. And the split right here in between is 0.5, which matches this 0.5 right here. And so this seems to imply that wine with a lower acidic value, amount of acetic acid, is better, while wine that has too much acetic acid tends to be bad wine. So what you've seen so far from the applications is you may think that it's always just best to just use Shether-Jones and normal kernel, and that's a good conclusion for practical purposes. But thinking back, what we did is we actually fit everything using the normal kernel and the Shether-Jones, so it's sort of uncertain how well the scaling does, right? If maybe, for example, you fit using the Apashnikov kernel and maybe you get some other results, but it's sort of uncertain because those are pretty difficult to obtain. Thank you. I hope you guys learned some new things.